let's do another example of curve sketching following our 10 steps. First one again is to identify the domain and the range. For this particular problem, it might be helpful to rewrite it as x squared plus 1 or x plus 4, x minus 4. And again, we'll write that as f of x. The reason why this is helpful is because it shows us that our domain is, in fact, not all real numbers. So, union with 4 to infinity. And we say that because there's no issue with the x squared plus 1 on the top. That's just a polynomial. So let's keep going. Well, again, we'll worry about the range later because it can be difficult to ascertain the range without analyzing all these other pieces. So the next piece is to find the y-intercept. So when we plug in 0 here, which is valid, it's no issue here, then we get 0 plus 1 over 0 minus 16. So we get 0, negative 1/16. So that is our y-intercept. Now when we get our x-intercepts, we're solving when this is equal to 0. So we're trying to say x squared plus 1 over x squared minus 16 is 0. Now what we know is that as long as what goes in the bottom isn't plus 4 or negative 4, then we can multiply by need to plot the right-hand side, and the left-hand side will simply be a mirror across the y-axis. Now, the next thing we got to do is find vertical asymptotes. Now, since we have a polynomial divided by a polynomial, and this is important, and this is completely reduced, right? There's no possible way to cancel any other factors because this doesn't factor. So since this doesn't factor, none of these can cancel. What that tells me, if I have a polynomial divided by a polynomial, then each of these is going to be a vertical asymptote. And again, we knew that because if we get one asymptote for a positive, we're going to get the negative case because of the reflection, because it's an even function. Now for a horizontal asymptote, if we apply, again where it's even, we only have to worry about the limit as it goes to positive infinity. We get 1 because if we take the limits here, they're going to reduce to 1. Okay, so then by taking that limit, we're going to get, as it goes to negative and positive infinity, the asymptote's going to be at 1. So the next thing we want to do is let's get derivatives, and then we can go from there. Now, what we can do for this is we can rewrite f of x as 1 minus 17 over x squared minus 16. because we could because that's technically x squared plus 17 or plus 6. Hold on. Sorry, plus 17. Because this is x squared minus 16 over x squared minus 16. So we can, because 1 splits into negative 16 plus 17, so that allows us to write this as 1 plus 17 x squared minus 16, or 1 plus 17 times x squared minus 16 to the negative 1. The reason why we like to do that is because it's going to make taking our derivative easier using the chain rule. So f prime of x, the 1 is going to derive the 0. The negative 1 is going to come down, so you're going to have negative 17, and then you're going to have x squared minus 16 to the negative 2, and then the derivative of the inside is 2x. So that's, you can rewrite that as negative 34x, x squared minus 16 to the negative 1. Now that you've done that, what you can do is you can take the second derivative. So we can do that using the product rule. So we take the derivative of the first one. Oh, that's negative 2. Leave the second term alone. And then you have the first term. And now we take the derivative here. So negative 2, x squared minus 16 to the negative 3. And then multiply by 2x. So that becomes negative 34 over x squared minus 16 squared, and then this all multiplies out, so that's 4 times 34 is 136, so that's negative negative makes a positive, plus 136x squared over x squared minus 16 cubed. So to get a common denominator of x squared minus 16 cubed, we have to say negative 34 x squared minus 16 plus 136 x squared minus 16 cubed, which we then, you'll get some cancellation here with those x squared, so that'll be that'll be 102 x squared, and then you'll have 102 x squared plus 34 times 16, so that's 480 plus 64, which is like 544. That can't be right. Maybe it is. 544 x squared minus 16 cubed. All right. We take one moment here. Something seems wrong here. So when we take the derivative here, we get a negative 17. This 2x, you get negative 34, no problem. You take this, that goes away, you get negative 34x. Bring down the negative 2, have here, so you have positive 136 minus 34 minus 34. Okay, that's right. I'm sorry. I had Momentary lapse in judgment. See, what's good is to just kind of inventory what's going on. So, kind of full disclosure on what happened here is I looked at this and I said, well, this is always going to be positive. And I know from looking at this that we're going to have behavior where it's concave down. Because if this was always positive, it's going to be concave up. And I'm like, there's no way. And the reason why I thought that was I have this x squared here, but then I was thinking about this like a squared, because that would always make that positive, unless it was 0, but it would make it positive all the time, so you'd have issues. But that's cubed, so it's not going to. So again, this is always good to inventory your process. Always good to inventory your process to give yourself just some sanity checks, man. Sanity checks are huge. Okay, so now we have these derivatives. So we need to find critical points. So if you look at this function here, which I'm going to rewrite this now as negative 34x over x squared minus 16 squared. If you look at this, it's very clear that 0 is a critical point. And if I plug in f prime of 0, I have, or f double prime of 0 is 0 plus 544 over negative 16 cubed. Well, negative 16 cubed is 4096, something like that. So that's going to be 544 over negative 4096, which is negative. So it's that concave down. Since it's that concave down, that tells me that 0 is a local maximum. That's the second derivative test. Now, we do also know that the derivative fails to exist at positive 4 and negative 4. So we know that it fails to exist at positive 4 and negative 4. So we're going to have negative 4, 0, positive 4. So we have to pick points in between to determine if it's increasing or decreasing. So we're going to pick 1 and 5. Now we don't have to pick on the left side because we know it's an even function. So we're just going to mirror. So then f prime at 1 is negative 34 over negative 15 cubed. Well, that's negative and that's negative, so that's positive. And f prime at 5 is equal to negative 170 over 9 cubed. It's less than 0. So at 5 it's decreasing, at 1 it's increasing. Or yeah, between 0 and 4 it's increasing. And after 5 it's decreasing. Now is that correct? No, that's not correct, because these aren't cubed. These are squared. So in both cases it's decreasing. Well, sorry, that's not how that works. I'm sorry, that's not how it works. Since it's reflected on the other side, it's actually increasing and decreasing. And you're going to say, well, I thought you said that the behavior was reflected, and it is. Think about this. If it looks like it's sloping up on this side, it's going to be sloping, like, to look the same, it looks the same this way, but going left to right, it looks like you're sliding up. Going left to right, it looks like you're sliding down, even though it's the same picture. So it's increasing, increasing, decreasing, decreasing. Okay, so 9, 10. We've got a maximum and we've got that it's decreasing there. So then what we see over here is that this has no value for which f double prime is equal to 0, because that numerator is never 0, because it's squared and then a plus. It fails to exist when x is plus or minus 4. However, it doesn't really exist there, but we'll go ahead and partition that out. So we'll say, all right, so we'll pick 0 and we'll pick 5. So f double prime at 0 is 544 over, we already know what it is. F double prime at 0 is already this. We know it's less than 0. So we know that it's concave down. And then from f double prime at 5 is, f double prime at 5 is this bad boy. It's huge. It's some sort of positive number on top. I don't know what that is. Some positive number. And then that's 25 minus 16, so that's 9 cubed. So that's greater than 0. So that's concave up, and that tells me that that's concave up. So now we know that we don't really have any points of inflection. I mean, technically these are points of inflection because they change concavity, but they're not points of inflection the way we typically think about it, where it's some kink in the curve. You're going to have an asymptote there. So on one side of the asymptote it's going to be concave up, on the other side of the asymptote it's going to be concave down. So knowing that, let's do all this. Now there's an additional piece here that I haven't mentioned before, which is that sometimes it can simply be helpful to plot additional points. That's not really part of the 10-step process, but it's a pretty good idea in general to, if you have all of these things together, it can still be helpful to plot a few random points. You know, you can pick like x equals 1, right? You do that, you're going to get 2 over negative 15. It's not that hard to do. You could pick, you could pick 3 as well. You get 10 over negative 7. You get some points to kind of help fill in the gaps. But anyway, so we know that negative 4 and positive 4 are not in the domain. We know that 0, negative 16 is a point. And we know that that point is a local max. We don't have any x-intercept, so it never touches the x-axis. We know it's an even function, so as long as we draw this side, we get that side for free. We have vertical asymptotes at plus or minus 4. So let's draw the plus 4 case. We have a horizontal asymptote at y equals 1. We have the local max here. Now and then we have that it is concave down from negative 4 to 4. So we have that here. So it's concave down and decreasing. So from 0 to 4, we know it's decreasing, concave down. So it's decreasing, concave down. So we know that it's reflected. So it looks like that, decreasing, concave down. And then after the point, so you might ask yourself the question, once I'm over here, am I above the asymptote or am I below the asymptote? So what we might want to do is take like f of 5. So f of 5, if I plug that in, I get 26 over, looks like 9. Which is greater than 1, so I know that I'm up here somewhere. Tells me I'm up here somewhere. Now I know that I'm decreasing and I'm concave up. So not only am I going down, but I'm going down concave up. And again, because it's an even function, I know that it behaves the same over here. And so that's how you draw this type of problem, given what you, I think that's everything we need to know to finish out this problem.